Okay. You should be able to see the screen. Can someone confirm?
Yes, sir, we can see.
Okay, wonderful. So let me start sharing. So what did we see in the last few lectures? We looked at function definitions, applications, anonymous recursive functions, tail call optimization, partial application, and so on. But all of these concepts can sort of be combined under one bag called functions, right? So when people talk about functional programming, you might be misled to believe that it's all about functions. It is, but in practical functional programming, there is also a very important missing piece, which we haven't seen yet, which is the ability to define data types, right? So, what do these functions operate over? They operate over data types, and one of the real power of functional programming is to be able to define data types which precisely capture your intuition in mind without all of the craft, right? So I think the thing that distinguishes um, how we do data in functional programming compared to, say, object-oriented or say imperative programming like C is the precision and um, the concise nature of how you can express data, and the fact that you have very expressive functions to operate over data, and that forms the very powerful combination. So it's functions on one hand, but also the ability to define data on the other hand. So these two sort of combine to give you a lot of power, right? So we've seen functions. We'll see what we mean by data types and data. So this is going to be the focus of this particular lecture. Okay. In particular, we are going to look at two concepts. One is how do you construct data, right? How do you put together little pieces of information so that they form something that is useful? And how do you deconstruct data, right? So how do you pry it apart in a meaningful manner so that you can extract what is inside, right? So it's not just sufficient to be able to construct a beautiful thing. It is also important to be able to access what is inside the constructed data very easily and quickly and appropriately. Yeah, so this is high level topics, but we will sort of see what I mean. But um, this is going to be the focus, right? The focus of putting together is going to be data types, and focus of prying it apart is pattern matching. So we'll see what we mean by that. Actually, I'll clear my notebook. Right. So there are a bunch of meta thing, right? So there are a bunch of commands here which will help you sort of um, play around with the notebook. I'm sure you might have seen this already. You can change the kernels, right? I'm using OCaml, but this course also uses Prolog. So we have a Prolog kernel as well. So if you switch this kernel to Prolog, you can do Prolog right here in the notebook. There is Python 3, which is the default one that comes installed. And if you want to clear all of the output, you can go to kernel and restart and clear output, which will sort of clear everything out and you can go ahead. There are also other things. This setup is quite powerful. Okay, so I recommend looking into what is available and what you can do with this. So that said, we'll jump back to where I was. So, okay. So in OCaml, you can define new types, right? New data types, but also just new types. The first thing you can do is define type aliases. What are type aliases? Aliases are just a name that you give for existing types. Okay, so they're just like another name. So here is an example, right? So so this particular definition refers to a tuple, right? It's a pair. It's a pair which has it's a type, right? And the type has two components. The first component is an integer, second component is a floating point number. And this is a valid type in OCaml, right? And OCaml allows you to define new names for existing types. And the new name here is int float pair. I'm just giving it a name called int float pair using this keyword called type. So type some name equals some other type just defines a type alias. Okay, so if I run this, I'll just get the same thing again. What OCaml is telling me is, oh, you've just defined a new alias for instar float. Okay, so of course OCaml has type inference. So when I say let x equals 10 comma 3.14, it looks at each of the values and then infers the type. It looks at 10, it's an integer. It looks at 3.14, that's a floating point number. And we are putting it together using brackets and comma. So it must be a tuple. So the type inferred for x is instar float, right? So that's the inferred type. But you can use this syntax. We've seen the syntax very briefly in the second or third lecture. This is basically informing OCaml type checker and the type inference engine. Oh, rather than you inferring types for this, just just assign this particular type, right? This is not typecasting, right? So that's the first thing. That's the only thing that you have to remember, right? I'm not casting this string to an integer or something. That won't work in OCaml because that breaks type safety. What I'm trying to do is to just name the type as something else. And the only thing that you can do here is use equivalent types, which is just the aliases. So what I'm doing here is I'm taking x, which I know is the instar float, and I know that instar float has a different name called infloat pair. So I am just saying let y equals infloat pair. And if you run this, OCaml type inference engine has been told to record y as infloat pair. Okay, and the only reason it allows this is because infloat pair is the type alias for instar float. If I do anything else, it will break, right? So if I do this, then it'll break. In particular, OCaml doesn't allow you to do any sort of typecasting. There's a very deep reason for this because OCaml has this very nice property called type safety. We will sort of come back to this idea again. But just to give you a preview of what this idea is, if the OCaml program type checks, if the compiler says your program does not have a compiler error, then your program will not segfault, right? There is no segmentation fault by definition if your program type checks. This property is called as type safety, right? OCaml is not the only language to have type safety. So Java has type safety, right? When you compile Java programs, if Java program says um, everything is fine, I can produce a class file which you can load in your JVM and run it, then Java program assures that there cannot be any segmentation faults, any crashes, any memory errors. This can seem like a very abstract concept, but whenever I say memory error, think about security errors, right? Think about attackers stealing your password. Think about attackers stealing your bank account information, right? That is not present. Static types are one way to get there. You can also do this with runtime type checking, where you actually go ahead and check the types all the time at runtime. This is what Python and JavaScript and Ruby and other languages do, right? So you can achieve type safety both with static types and dynamic types. And the language, for example, which doesn't give you type safety is C, right? In C, you can write anything, you can do casting happily, and C will accept it. You are in control. You are in the driver's seat in C, right? So the point of this digression is that's the reason why you can't automatically typecast anything. So you can't just go from instar float, which is a pair, to say now just consider this to be an integer. That will not work. You will often face this problem in OCaml when you're writing. You're often fighting the type checker, but type checker is actually doing a lot of work for you, right? It's statically removing a large class of errors that are possible. Okay, so that's the reason why this wouldn't happen. And that's the reason why int doesn't work, but infloat pair works because infloat pair is just a type alias. Okay, so type aliases are fine. Um, OCaml has other ways of structuring data, right? Tuples are one. That is one way to take smaller types and construct larger types, right? But it's also useful to actually name each of the components. So tuples have two components, right? But you can have like 7 components, 8 components. If all of them are integers, you need to sort of have some information about what each of those 8 components are. And records are a very useful mechanism for that. So records in OCaml name represent a collection of named elements. Okay. So here is an example. Here is a point that you want to represent in 3D space, and each coordinate is an integer, right? So here I'm defining a new type. I'm actually defining a new type called point, right, which contains three components, x, y, and z, and all three are integers. So there's a question: is this a struct or different? You can sort of think about it as a structure. It will look similar to a structure, but the similarities stop there. So it's um, think about it as a structure, but your analogy will break down very soon. Um, it will work like a structure, but it's much more powerful in terms of safety and so on. I'm not going to expand beyond it because the analogy doesn't hold. But yeah, but for a start, you can think about this as a structure, right? This will be where you would use a structure in C. You can use records, right? So this defines a new type called point, which has 3 labels, right? X, Y, and Z, and each label has a type. All three are integers. And this is just syntax, right? You have to sort of remember the syntax. So there is a type, there is open curly braces, close curly braces, and semicolon to separate the label. X, Y, and Z are just labels, and these are types. Okay. So yeah, and you can create and access records using open curly braces and dot operator. So this is similar to structures, right? So I'm going to define origin in a 3D space. So I'm saying x equals 0, y equals 0, z equals 0. Of course, you can. So the reason I put y first is this could be in any order. It doesn't matter. Okay. So yeah, this will work, and you can access the individual elements of the record using dot and the label name. So I'm going to access the y field of some r. So I'm defining a function. Let get y is a function that takes a point and then returns the y field of the record. So r dot y gives you that. So observe that I'm not writing any type here. Just by the fact that I'm using dot y here, OCaml infers that r has to be a point type. And you will see that it infers the correct type. So origin is a point because I've used all three fields, but also the fact that just because I use dot y here, where y is a label, and y label is part of the point type, record type, it infers the type of R to be a point. Okay, so there is a question in the chat. Can I do let y equals int 4 divided by 2? Why don't we try that, right? So just a digression, right? So there's a question. So so all of these questions, right? You can just try it out. I'm just going to show you how to do this. So this is fine. So this works because slash is an integer division. Okay, so 5 divided by 2 will be 2. And it's not doing floating point division. And floating point division, you have to do dot. This may look weird, but you'll get used to it. 2.0. This won't work because this is floating point, this is integer. So you need to name this as float, and this will give you the right value. Okay, so I think that should answer the earlier question. What if there are two records which contain the same member variable and the same name? Really good, sir. If we hadn't defined a point, what would happen? Actually, the last question is easy. So if you hadn't defined the point, then OCaml would complain. Okay, so um, get let's say a equals r equals r dot a. So OCaml would just complain saying this record field is unbound, right? Because it doesn't know. The previous two questions are interesting because think about shadowing, right? So all that happens here is shadowing. So those are really good questions. So what if y happens to be a label that is defined in two different records? So everything is lexically scoped. So whatever comes second, the latest in the lexical scope will be the one that is chosen. So I have point defined here, right? Let's assume point is point 3D. Let me define a point 2D here. So I'm going to do type point 2D equals x is an integer and y is an integer. Okay, so I've defined point 2D. Observe that x and y are both present in the point and point 2D. And now if I do let get y r equals r dot y, the inferred type is going to be point 2D int. Because what is happening, the reasoning is that this label, the new label that you have defined, is shadowing the previous label. So when you refer to y here, you are referring to the label y in the closest scope. So point 2D comes after point, right? Point 2D comes after point. So the y chosen is going to be the y in the closest scope. But the interesting bit is Z is still available, right? I haven't sort of shadowed Z. So if I do Z, it will refer to point. Right? X and Y are going to be point 2D. X is going to be from this type. Y is going to be from this type. But Z is not shadowed, so Z is going to come from the previous one. Typically, we tend to not name the same thing again, right? So we tend to keep it separate. We have other methods of namespacing, essentially. So this problem doesn't occur in practice. If you're worried about, oh, this is going to confuse all sort of things, in practice, this doesn't occur too badly. So can we not access point x and you can, right? So see, the thing that is happening here is OCaml has a default way of um, sort of going with shadowing, right? If you really want to access the 3D points X, one thing you can do is you can say R is actually a point. Don't infer, right? So what I've done is I'm instructing OCaml to say, don't infer the type automatically. I'm just going to say R is actually a point. So this will come in handy. So to be, just so that people follow along. So because I am giving an explicit type here, OCaml knows that this is going to be a point, and this is going to return the X variable there. If I don't have this type annotation, it's going to pick the most recent one. Okay. So, okay. So this should answer some of your questions. So let me remove all of this and then rerun this so that the rest of the examples work. Okay, let's switch to the presentation mode. Okay, so we were here, and so in functional programming, we tend to associate not mutability, but whenever you want to produce a new value of something, you actually produce a different value. And functional record update is one way of doing it. So assume you have a record which has like 20 fields, and you want to um, copy all of the fields, the 19 fields, and you just want to change one of the fields, right? So this pattern happens often. Um, actually, let me sort of be more precise. I use the word change. We are not actually making a change. So assume that you have a record with 20 fields. You want to create a new record value with the 19 fields being the same and one field being a different, right? So in this case, rather than repeating all of the 19 fields, so some r dot a, r dot b, r dot c, all the way through, there is a easy syntax for doing this. So here is the way to do it. It's called a functional update, but actually there is no update going on. It's creating a new value. So what I'm doing here is I'm taking the origin record value and I'm saying I'm creating a new record value where all of the fields are same except z field, right? So I'm copying all of the fields except z field, and I'm creating a new record value called p. So uh, recall that origin has x equals 0, y equals 0, z equals 0. So this should be x equals 0, y equals 0, z equals 10, which is what you have here. And the reason why I'm trying to be precise about change and update and all of this is origin remains unchanged, right? That's the key point. So when you just look at origin, it still remains 0, 0, 0. So there is no update going on, right? You're just creating a new record. And this with syntax is a way to just create a new value, new record value, where one of the fields is changed. If you want to change more than one field, you can just do semicolon 20. So again, so the one field x is retained, two other fields are given new values, right? And you create a new record with those values. So we have the value here, but the original thing remains unchanged, right? So this is useful because sometimes you will use a large record and you just want to create a new value where one value is just changing. So this syntax is helpful. Um, OCaml does, so at this point, I'll just say OCaml does have mutability. We will come back to mutability later in later lectures, but there is a clean separation between the immutable world and the mutable world. So I'm just, whatever I'm showing here is completely immutable. I'm not changing, destructively updating any memory location, right? I'm not changing a pointer to some other value. I'm just creating new value whenever I say this functional record update. Okay, so that's this syntax. And I think the last thing in records is the special syntax for creating records. So let's say I have a function, right? Make point, which takes a x, y, and z, and then returns you a record which has x, y, and z. So the function, you can define it like this. X equals x, y equals y, and z equals z. So this is going to take three integers, right? And it's going to return a point. But you can see that there is a lot of redundancy, right? X equals x, y equals y, and z equals z. And you may see this form uh, where you just, if x equals x is your syntax, you can just replace that with x. So this concept is called field punning. Again, this is just a helper thing, right? It's not a primitive, nothing fancy going on. Whenever you see something like this, you just assume that, oh, we are naming the same field like that. But the names have to be the same, right? So you have to have a variable whose name is the same as the label that is used in the record field. And if it is the case, then you can do this. And these are exactly the same. They have the same semantics, right? So this, both the static and dynamic semantics are the same. This is just a syntactic sugar. So what happens is the compiler, the first thing it does in early phases is actually convert internally this syntax to this syntax. And then it actually goes and type checks, right? So it's just convenience. So nothing critical going on here. But you might see the syntax in some of the assignments later. So I just want you to be aware of this particular syntax. Okay, so we've seen two things so far, right? We've seen tuples and we've seen records. And they sort of are, if you sort of take a step back and stare at them, they're actually the same thing. They're both what are known as product types. A product type is a value of a product type is one where we include each of the values in the constituents of the product, right? So let me make it more concrete. So here is a definition of a person record, which has a name, an age, and a height, right? Name is a string, age is an integer, height is a floating point number. And you can also define it equivalently using tuples. I'm just defining a type alias here, right? Type %t is string int float, and I'm not naming each of these labels, right? So in terms of expressive power, not in terms of syntax, right? In terms of expressive power, both of these are the same. The only difference is that whereas records are indexed by names, right? Where labels, the tuples are indexed by its position in the tuple. So name is the first one, age is the second one, float is the third field. Here we just index by the label, right? So you can sort of, so what do I mean by this idea of they are both same in the expressive power and so on? So of course, the syntax is different, right? So syntax is different, which means you can't happily change record to a so one record instance to a tuple and then expect the rest of the program to work. What I mean is something more fundamental, right? What I'm saying is if you have a program which uses tuples extensively, right? So if it say has some tuple that represents a row of database record, some it has say 10 fields, and all of these are integers. You don't know what those integers mean, right? So at that point, you can actually replace that with a record for better readability, right? Without fundamentally changing how the algorithm works, because they are both representing the same information, right? Where one is using positions as indices, another one is using labels, right? So these sort of types are known as product types, and OCaml has two product types, and these product types are records and tuples. So in functional programming, you will see a lot of terms, right? I don't know why, because I work on functional programming. We tend to create these sort of mathematical terms which um, don't have any particular reason why they are called that. There is a reason for product types, um, but you'll often see these terms used back and forth. Just get used to the term, right? So there is no particular reason why we pick these terms. There might be reasons, but it gets lost, right? So product types are just product types. Don't ask me why they are product types. I can give you an answer, but I think sometimes it is just like take this term. These are product types. Go along with it, right? But we tend to use a lot of terms. It just so happens. Yeah, it sort of adds some mystique, but also sort of makes it hard for newcomers to actually learn the concepts. But these concepts are very simple, right? These are just names. When you can name certain things, you can sort of talk about them to a third person, right? You can have a conversation about certain abstract concepts, and that's why we like names. But you'll get used to a few names after a while. So these are product types. So if you think about product types as multiplication, right? If there's a multiplication, is there a notion of a sum type, right? Where the way that you put together data is the addition. In fact, there is. Actually, this is one of the most important concepts in all of functional programming. And this concept is also slowly coming into Java, and Rust already has this concept. So any modern language in the next 5 years will have this concept, right? These are called variants. And what are variants? If you sort of have this analogy where product types are the same as structures in C, then variants are similar to enums in C, but they're of course much more powerful. So you can start there and then sort of look at the detail. So what are enums in C? Enums are just labels, right? So the value could be of one of the several options. The same thing happens here. Variants have a type name, right? So you start with the keyword type, you give a name for the variant, and then what we have are a series of options, right? So these are a list of options, and these options have multiple components. So the first component is called a constructor, right? C1, C2, C3, C4 are constructors. You can sort of think about them as the labels that you would use in enums, right? If you just recall C enums, those are just labels. But unlike C enums, where you just have the labels, you also have um, a data, an optional data that is carried by a constructor, right? So this could be, so C1 is a constructor that carries type T1 internally. So rather than thinking about them as labels, you sort of think about them as um, naming each box, right? Each of these um, options is a box with a specific name, right? The name is the constructor, and the contents in the box could be an arbitrary value. So this could be any type that you can imagine in OCaml. So I'm just writing T1, T2. This could be T3. I don't know why I wrote T2 here, right? So that's the structure of defining a variant. So to translate from C, they are like more powerful enums where the each of the labels can carry some value, right? So that's the high level description. These are also known as algebraic data types, right? So we tend to use the term algebraic data types a lot more than variants. So variants we use in pragmatic context, and algebraic data types in more formal contexts, but both are the same idea, right? So yeah, okay. So let's look at an example, right? I think looking at examples actually make things much clearer. So here is something that you might have used C enum for, right? I'm going to define a type called color that has three labels. So red, green, and blue. I define three colors essentially. My whole color landscape just has three colors. So when you do red, green, and blue, you actually define a new color, new type called color, which has three components. And now OCaml knows about this particular type. So it can do type inference on this newly defined type. Right now, if I define let v equals green comma red, it infers the type to be color star color. So each one is a value, right, whose type is a color, and then I put these values in a pair. So I get the pair type here. So I get the pair type, and these are colors. And of course, you can have um, more of these, right? So it doesn't matter um, what is uh, what is each of these components. You can also mix it up because so that's fine. That is all fine. So the thing to take away is um, so green, red, and blue are the defined colors, right? There is no yellow that I define. So if I just do yellow, so OCaml says that it doesn't know anything about the constructor called yellow because we haven't defined it as part of any type. Um, and yeah, so this is sort of helpful because we cannot define labels uh, just on the fly. Whenever you use these constructors, OCaml actually knows what the type of that constructor is, right? So that is quite important for type inference, and this is what is happening. It doesn't know anything about yellow. And one thing I forgot to mention about constructors is they all start with a capital letter, right? So the constructors have to start with a capital letter, and that's how OCaml knows that it is a constructor. Yeah, okay. So let's put it back to blue. So here is more complicated use, right? So that was just a enum use. What else can you do with these constructors? So now let's define a point, which is a point 2D, right? A 2D point with X and Y, which is record. And then I want to define different shapes, right? I have a collection of shapes. First is a circle, second is a rectangle, and third is a colorful point, right? And I define a new type called shape, right? This is a variant type. It is one of these three things, right? First is a circle. A circle has a point, which is the center, and a floating point, which is the radius. Okay, so just look at the syntax. So this is sort of, we use this thing called off, and off is sort of defining the, it's separating the constructor name from the contents in that box, right? Circle is a name of the box, right? And inside that box, you'll have a tuple, a pair, which is a point where the first one is a center of the circle, and the second one is the radius. And similarly, the shape could be a rectangle, in which case it is meant to be composed of 2 points. The first point refers to the lower left, and the second point refers to the upper right. This is, all of this is just semantics that we ascribe, right? The type itself doesn't say anything about it. It just says it's a point and a point. This is how we define a rectangle. And the third one is a color point, which has a point and a color. So color is one of the things that we defined earlier. Red n equals n plus 1. So the question is, can I define a function called red n? You can't name it with functions have to start with the functions cannot start with the capital letter. So there is a question where if I do this, what happens? Yeah, so this won't work. Actually, let me try something else. Yeah. So whenever OCaml sees something that starts with a capital letter, which is not a keyword, right? So this is sort of a thing that is going to look for what sort of a thing it is. Whenever it sees something starting with a capital letter, it assumes that it is a constructor, right? So the example that you defined in the chat, right? That's not going to work because that's not a valid OCaml thing to do. But you can think about something else, right? If I define a different color where I also use the same constructor, that will get shadowed. So the shadowing works that way. Okay, so let me get back to where I was. So I was here defining a shape which has a circle, a rectangle, and a color point. Okay, so the type fully describes what I've just written, right? So it says there is a point, there is a circle, rectangle, color, point. Now I can define values happily, right? So now I can say, oh, circle is a value. This circle has a center at 4,3 and a radius of 2.5. So OCaml, by looking at the construct a circle, knows that it is a shape, right? And expects the first component to be a point, the second component to be a floating point number. All of that work out, right? That is why OCaml is actually allowing this value to be a properly typed value, right? If I change this to say 2, it won't work because OCaml has this type information floating around, right? And it says that this expression has type integer, but an expression was expected of type float. It is able to say this because of the types that you've defined here, right? It's doing type inference. I'm not prescribing any type here. I'm just defining values, but OCaml is able to automatically infer all the types. Right? Similarly, I can define a rectangle here. Rectangle has 2 points, and this gives me a type called shape, right? Type a shape, and then this is the value. Okay. So can we assign variables values from constructors using let? Yeah, you can. So can we assign variable values from constructor using let? I think the question is, so does this answer your question, Sarthak? Okay. So can we omit X and Y? You can't, right? So The problem is that because you can, because the labels, okay, so you can't omit X and Y because records are indexed by labels. So they are not positional, right? You can move them around. So I can write, so this is also X equals 2, Y equals 3. So if you omit the labels, I don't know which one is X and which one is Y. So that's the reason why you can't. Is there use of combining the three constructors into one type instead of declaring separate types? Yes, there is, right? So if there are only three shapes in the world, right? So, and you want to say, I want to define the whole world in terms of shapes, and they can be in one of these three shapes. There, you actually want to say the world is a collection of a set of shapes, right? And each shape could be of one of these three things. So, if you define three different types, you want to define the world as a set of something, right? And that something can't be like three different things. So you want to put them together, and uh, that is why the shape type actually helps you. Um, does that make sense at all? Right. So you want to give a name for these three things, right? I have three things. It could be one of these three things. I just want to give a single name for these three things. The name that I give is shape. Um, and I can define the whole world to be a set of shapes. Is it somewhere like an inheritance? There is no inheritance going on here, right? So this is just static. Um, everything is being structurally defined. So this is more similar to basic structures in C, right? No classes. So I'm when I say color point here, this is a point which refers to the point that I've defined here and the color that I've defined previously. There is no inheritance. So so this is not OOP, right? So even though we are defining these types to be structures, so inheritance is sort of different from just the structure of things, right? Inheritance sort of defines you the way you can extend certain things in one form, but this is not inheritance. Let me not go too deeply and pontificate about what inheritance is. Sir, what happens if I define let get area shape equals some definition related to rectangle? Yeah, you can. I will come to that, Raghu Raman. So you are asking a really nice question, right? So you want to, let's just pontificate about that question for now, right? So um, I'm going to define a function called let get area, right? So I'm going to let get area r shape, and I want to return something here, right? And because this is taking a shape, it could be of three things, right? I can define a area for a circle, area for a rectangle, but I don't have area for a color point. I need to sort of decide what I want to do for each one, right? Once you define it, we will see mechanisms. We will come to pattern matching, right? So I'm sort of not giving away that. But the first thing you need to think about is what is the area of the point. Are you going to say it is zero or it is an error? Because like what's the area of, you need to decide that first before you can define that function. But you can define that function, right? But not just related to rectangle. You have to decide on what you're going to do for both circle and the color point, right? We'll come to some of this a little bit later. So another question, can we define a function which takes arguments of type shape now? Yes, you can, right? So you can um, define functions. So let's see. For now, what I'm going to do is I'm going to define a stupid function, um, which is because I don't want to give away the rest of the things. So this is a function which takes a shape and returns a shape. It's not doing anything interesting with the shape, because in order to do anything interesting with the shape, I need to show you something else, which we will cover in the next class. Yes, you can define functions which takes arguments of type shape now. Okay, so before I actually show you how to, some of these questions, right? The last two questions, what happens if I define get area, and can we define functions with shape? These relate to taking the type apart, right? I sort of constructed the shape thing. I say my world is full of shapes and it's a set of shapes. I also need to be able to go into a shape and say, if it is a rectangle, get me the area of the rectangle, right? Which is what Raghu Raman is asking. Of course, I want to do that. But before I go into that, there are few more interesting concepts in order to put together shapes. Let's look at that. So, so far, what we've been doing is whenever we define a shape, we've been sort of referring to other types, right? But think about linked lists, right? When you define a linked list, you have a node definition which has a value, right? And then the tail refers to the same linked list type that you're defining, right? It's a recursive definition where you say the type that you're defining has a component which is of the same type. And this is called a recursive variant type. And this is quite natural in OCaml. So here is a definition of an integer linked list in OCaml, right? I'm defining the type int list, and it has two constructors. So the int list could be of one of these two things. It could either be an empty list, in which case I say I nil, right? Or it could be a non-empty list. If it is non-empty, then it contains an integer value and another list. So it contains an int list again. So this is, you can sort of view this as your next pointer in a node definition, right? So I've defined both of these. So I have a int list definition. Now I can actually define the list here. So just before I go to this, so here is a list, right? This is a list which contains nothing. It is equivalent to a list which is empty, right? Here's a list which contains just one. So icons, I nil. So here is a list that contains one node, and the content of that one node is one, and the next is nil, right? And you can keep building this over icons to I nil. So here is a list that contains two, and the next node contains one, and that is the entire list. And I can keep expanding this, right? Icons 3. Yeah, so you can keep doing this. These are just values, right? And just to show you, these are regular values. I can define let x equals in icons 3 comma x, right? So this is just a value which defines a list with two nodes. The values of the nodes are 2 and 1. And I'm using that list in another, constructing a new list, right? Where I have 3, and the tail of the list is going to be this list x. Okay, so you can do this, and the types are automatically inferred, right? Once you have the definition, the type is automatically inferred. What is the type of inil? Just look at this one, right? Inil is a constructor in the type int list. So inil is a value. It's just a value. If you do inil is just a value, and the value's type is int list. Does that answer your question, Venkat? I think I'm going to stop here, and I'll give a few minutes for questions. Sir, but the value hasn't been defined before. The value is defined, right? When you define the type, you are actually defined the constructor, and the constructor name is the value. How does it infer its type? Because this constructor is being defined in this type, right? what I'm saying when I define this type definition is, OCaml, I'm going to tell you there is a new type called intList, and it has two constructors. The first constructor is a INL, and the second constructor is icons. So whenever OCaml looks at INL, it knows that that has to be of type intList. Does that make sense? I'm actually telling that intList is a type with two values, right? INL is a value, icons is a value, and this yeah. So for example, this is not a value, right? If I just do this, it's not a value because in order to construct a value of using the constructor icons, I actually need to provide the contents as well. So it's saying icons is a constructor that expects two arguments, right? But it's applied to zero arguments here. And the same way, I can't do say 1, 2, 3 here. That would be bad because the types don't match, right? It expects two arguments, but I'm giving three. And oops. Also, I can't do say 1, 2. The number of arguments matches, but the types don't match up. So I have to be, because I'm precisely defining what the type is. The type inference actually helps me to um, get the program right. Can we differentiate between constructors of the same name on the basis of arguments? No, I think the constructor names uniquely define the recipe for type inference. So there is no constructor overloading, if that is what you're asking. So I can't have two constructors which take two different types. A record of user-defined constructors. Yeah, you can, right? So you can, those are just values, right? So you can, so can we have a record of user-defined constructors? Yes. So let's say type R equals A is int list and B is int list. Okay, and then I can do let V equals A is INL and B equals icons of font. Yeah, so it's a record of user-defined constructors. So these are just types, right, which is expected, and these are just values. And so you can put them together. Any other questions? Okay, so then I'll stop here, and then we will continue on Friday. All right, thank you very much.